Okay, so I'm going to look at some of the calculation parts of the recent test on cosmology. So the first one was looking at a diffraction grating. So we can see that we've used it to look at a spectrum of light, and we've got different fringes appearing with different colors depending on the wavelength. So we see we've been given a bit more information, so we know the angle between the two blue rays and the angle between the two red rays. So that will allow us to figure out what the angle of each of those orders is from the central maximum. And we know what the number of lines per millimeter is on the diffraction grating, which will allow us to figure out the slit separation. So that's what I've done first. I've figured out what the slit separation is. So you first need to convert it into lines per meter by multiplying by 1,000. And then you need to take the reciprocal of that to find out the distance between the slits, which I've done there. The next thing I've done is figure out what the angle of each of the fringes is to the central maximum by halving the values, and then we're just using the diffraction grating equation with those values to calculate each of the wavelengths there. I just realized down here at the bottom for some reason I forgot to change it and it still says blue. That's clearly meant to be red down here, but that's how we do that one. Okay, so the next question is looking at an energy level diagram of the hydrogen atom. So we're looking at the quantum model of the atom here, and we've got some different energies. So we know what the energies are at ground state and the excited state as well. So it wants us to determine the wavelength that we'd get from an electron transitioning from E3 to E2. So the first thing you need to do is work out the difference in energy between those two levels, which is 1.89 electron volts. We then need to convert that into joules, because if we want to put it into an equation, it needs to be in SI units. So that's what I've done next. And then we're just going to use the photon energy equation to figure out what the wavelength is. And once you put all the values in, that comes out at 658 nanometers. So if we're going to a different transition, so it says E3 to E2, which we just calculated gives you a visible light. What would E3 to E1 give? Well, if we look at it, we can see E3 to E1 is a much bigger energy transition than E3 to E2. So the photon energy is going to be much bigger, so the wavelength would have to have a much shorter wavelength. So that would put it in the ultraviolet part of the spectrum instead of visible light. Okay, so we're looking at a plot of the different wavelengths we get, well, the intensity of the different wavelengths we get from 3 different stars. And what we can see on there is we've got 3 different most common or most intense wavelengths here. So in order to figure out which of them is the coolest, we need to look at which of them has the highest max wavelength or most intense wavelength here, because we're going to use Wien's displacement law, which says that the size of the most common wavelength, which is the peak of all these graphs, is inversely proportional to temperature. So if you have the highest max wavelength, you have the lowest temperature, so it's going to be A. If we then actually try and figure out what the temperature of star B is, we need to look at the graph to get our value of the most common wavelength. So I'm looking at that and I'm seeing 300 nanometers. And then we just use Wien's displacement equation, which is this one, to figure out the temperature, which I then round to 2 significant figures because the Wien's constant is given to us in 2 significant figures. We're going to go through a similar process in the next one. So we're looking at a different star, and from that we have the most common wavelength at 241. So again, we're going to use exactly the same equation to figure out the temperature of this given star here, which is 1.2 times 10 to the 4 Kelvin to 2 significant figures. And once we figured out the temperature, if we measured the luminosity or the power that it's dissipating light energy, we can in effect figure out what its radius or size is. So we use Stefan's law, which you can see stated here. We want to find the radius, so we need to rearrange to make the radius a subject. We need to multiply the luminosity of the sun by 120,000 to find the luminosity of Rigel, and then we can just plug in our temperature that we found before and allow us to figure out the size. So 5.6 times 10 to the 10 meters there. So that finishes the calculations part of this test. So I hope you found that useful. If there are any questions, please do comment on it and let me know. But thank you much for watching.